क्लिक करना है। इसको तो उसमें देखिए फ्री ऑफ ऑप्शन है, इससे आपको मोबाइल में उसके बाद यहाँ पे राइट पे टोटल नंबर यहाँ पे दिया हुआ प्रॉब्लम होता है, ठीक है। इसके बाद यहाँ पे देखिए आपको दो ऑप्शन मिलते हैं, एक न्यू यूजर और एक रजिस्टर्ड यूजर। अगर आप न्यू यूजर हो, न्यू यूजर को क्लिक करेंगे। अगर रजिस्टर्ड यूजर हो तो मैं यहाँ पे सिंपल न्यू यूजर के लिए क्लिक करूँगा। उसके बाद यहाँ पे देखिए लॉगिन और यूजर आई डी लिंक के लिए यहाँ पे कुछ डिटेल्स हमें यहाँ पे देना पड़ेगा। इसमें सबसे पहले यहाँ पे देना पड़ेगा पॉलिसी नंबर है, पॉलिसी नंबर को देना पड़ेगा, ठीक है। बर्थ और ईमेल एड्रेस पैन कार्ड का पेमेंट सिस्टम देना पड़ेगा। इसके बाद यहाँ पे जो आप जो प्रीमियम पे करते हो वो यहाँ पे देना पड़ेगा। उसके बाद यहाँ पे मोबाइल नंबर पड़ेगा, पासपोर्ट नंबर दे सकते हो। उसके बाद यहाँ पे आप मेल हो या तो मिलते हैं यहाँ पे मेरा जो पूरा डिटेल्स मैंने कर दिया है। इसके बाद मैं प्रोसेस पे क्लिक करूँगा। प्रोसेस पे क्लिक करूँगा तो देखिए मेरे से यहाँ पे दिखा रहा है, ठीक है, पैन कार्ड नंबर, मोबाइल नंबर, मेरा एड्रेस ये सही है। तो इसके यहाँ पे यस पे क्लिक, जैसे आप यस पे क्लिक करोगे तो यहाँ पे तो जस्ट क्लिक करने के बाद यहाँ पे देखिए इंटर योर वर्ड, ठीक है। यहाँ जैसे पासवर्ड जो है एग्जाम्पल के तौर पे दिया हुआ है, इस तरह से आपको यहाँ पे, ठीक है। जैसे समझ लीजिए अगर
We welcome you, sir. Dr. S. Nagesh Bhatt, sir. We welcome to this AICT STTP. Good afternoon.
Good afternoon, madam. Hello, am I audible?
Yes, sir. Audible, sir. We'll start the session in few minutes.
Yeah, sure.
Welcome back, dear participants. Now we'll have session on deep learning for a sentimental analysis. A practical session will be by Dr. S. Nagesh Bhatt, sir. So we welcome you, sir, to this AICT sponsored online short-term training program on machine learning and deep learning techniques for AI problems. Before hand over the session to Nagesh sir, I would like to introduce him. Dr. N. Dr. S. Nagesh Bhatt sir is working as an assistant professor in NIT, and he received BTech and ME from Indian Institute of Science, and he received PhD from NIT Warangal. And his research interest includes posterior regularization, topic modeling, semi-supervised learning, distributed computing, database systems, spatial database query optimization. And he worked as ad hoc faculty in National Institute of Technology, Varangal, and worked as assistant professor in Institute for Development and Research in Banking Technology, Hyderabad. And currently, now he is working as an assistant professor in National Institute of Technology, Andhra Pradesh. And Dr. Nagesh sir is also having a funded project, and he is jointly working on the project titled Distributed Center of Excellence for Blockchain Technology along with CDAC Hyderabad. Dr. Nagesh sir is having 18 plus publications in esteemed journals and in various conferences. Sir, I would like to invite you to take over the session and continue with the topic deep learning for sentiment analysis. Over to you, sir. Nagesh sir.
Yeah. Thank you, madam, for your kind introduction, and very good afternoon to all the participants. I see this is the last day of the FDP. Is it so, madam?
No,
Sir,
sir.
this is day five, sir, and tomorrow also we have two more sessions followed with one exam, sir. This is day five, sir.
Okay, okay, okay. So I think deep learning algorithms are covered from the beginning. I mean, I don't know the context in which I mean the kind of contents that are already covered. Can I have that quick info, because based on that I can tweak my content accordingly.
Yes, sir. On first day, sir, we have machine learning versus deep learning concept, and after that, participants are given insights of neural networks, and after that, exploring conventional neural networks for real-time practices session will also be there, and then essentials of deep learning and applications, then deep learning for face recognition, and then participants have gave some of the insights about plant disease identification using convolutional neural networks, sir. Then yesterday they had video processing techniques, and then capsule networks, and then morning they have a recommender system concept, sir. Now we have
Okay.
about a
Yeah.
sentiment analysis,
That's pretty much fine. I think I have
and we also had one session about speech processing also.
I mean, whatever I have planned does not have any overlap with the existing things that are already covered. And that's what I just wanted to make sure that whatever I covered is not, I will be covering, will not be part of overlapping with other contents that are covered already. Okay. I just to make sure that, okay. Thank you for your inputs. And I will be covering content related to sequence labeling. And its applications in the context of NLP. Okay, that's the content that I'm planning to cover. Uh, uh, and yeah, slight revision for my I mean affiliation. I have done my BTech from RVR and JC, and I have done my ME from IISc. So that's a slight revision for what you said, madam. And yeah, currently we have been working on machine learning to a larger extent, and also we are also working on spatial data related big data query processing. Because my earlier work was in database systems, and more of that is what we have been doing in spatial data analysis. With one of the PhD students, I have been working with that. Um, I mean, to fit to the context of this FDP, I will be covering the sequence labeling concepts, and then we will see some hands-on related to that, and yeah, some couple of examples I will give you to practice sequence labeling approaches, because the sequence labeling modules are usually they kind of fit different kind of learning approaches, and they're more complicated than the conventional learning algorithm, learning frameworks like classification, regression, and then ranking, and other things that people are familiar with usually. Okay, so most of the times when you're building a convolutional neural network, the objective would be to minimize some loss, and that loss is coming from a classification problem. Okay, so you want to build, I mean, even if it is a deep neural network or an adversarial network like GAN, the objective of the neural network is to classify. So even if you are dealing with a GAN, the objective would be to generate images of a certain class. Okay, and whether you are able to generate it is not or not, that is the error that gets measured, and that gets back propagated, and the neural network weights are learned in such a way that the the uh, the classification error is minimized. Okay, and when you're using neural network, the basic idea is that the problem itself is highly non-linear, and that's where you use neural networks. Otherwise, you can still simply use linear models like SVM. Logistic regression is also a not linear, but non-linear only, but it has some linearity, and it can be thought of as a two-layer neural network with just the weights versus the features multiplication as the basic operation. Okay, so to summarize, when the classification problems are simpler to deal with, and we will see in the initial slides what's the relationship between the sequence labeling problem and classification problem.
Uh, Excuse me, Dr. Nagesh sir.
Yeah,
Some yes, a noise and disturbance is coming from your surroundings.
yeah.
So,
I am just now seeing that, but just let's try to adjust to a slight different location. There is a lot of noise actually. Sorry for the, I mean, I don't have any control over the noise. Try to help, but yeah, I think it is subsided. Now I can continue. Uh, but I don't have any control over the, the outside environment.
Okay, sir. Okay,
So
sir. We can continue, sir. You can continue.
we are actually, I am sitting in fifth floor, and I don't know how loud this noise is.
Okay, sir.
And yeah, let me try to convey what I can add to the context of this workshop. I think this is visible for you, right? The slides are visible, right?
Slides are visible, sir.
Yeah, so sequence labeling refers to the task of modeling sequences to relate to their sequential label. So you're given with a sequence of observations as opposed to one single observation to be related to a single label, right? Instead of that, you're given with a sequence of observations, and each observation is associated with one label, and that is the nature of the task that you deal with when you're dealing with a sequence labeling task. And it's a type of pattern recognition task that involves algorithmic assignment of categorical label to each member of the sequence of observed values. Let us see what, with some intuitive example of how complicated or easy it is, or how useful it is in practical context. Let us see a couple of examples. Okay, so these are all some voice assistant apps that you typically see. One from Amazon, one from Microsoft, one from Google, and all of them are essentially doing some similar service as this scenario. Customer is calling a function call, and they wanted to see if the function call is available, and this is how the customer starts his conversation. Then there is an agent that is sitting there, and it tells how can I help you, like a human sitting. And then the customer will say, I want to book a call on 3rd April between 5 p.m. to 9 p.m. And you see that he's specifying some specific details about what he wants, and it is associated with some timeline. And this computer program or agent that deals with this person's interactions, it has to extract this information which is relevant for its further steps, and it has to pinpointedly give the answer by processing this data. Okay, so first thing is it has to identify what is the time, what are the parts of the sentence where this time is specified, and then date is also specified, right? So these are the things that this agent has to understand, right? And then let us say it understands that, then it will further tell, I mean, because the information that is provided, it is not sufficient to tell a decisive answer the agent cannot tell a decisive answer. Hence, it will ask further, may I know the number of people attending the meeting? Then the person has to respond back saying, let us say there are 50 members who are supposed to attend this meeting. Then when it looks back at the current, current occupancy, and sees that all the 50 occupancy rooms are all occupied, and then it will ask for a slightly different time slot. Okay, so revised time slot is what it asks for, and that's what this conversation tells. Okay, so it gives couple of options for the customer to schedule. The same slot is free on a different day, or we have the availability is there after 8 p.m. on the same day, or between 12 to 5 p.m. These are the timelines in which you can book if you stick to the same day, or the other day there is some other option that it gives. Okay, so ultimately the kind of conversation is sequential, and processing is also sequential, and this is the nature of a sequential task actually. Yeah, for the sake of time, I mean, in interest of time and so on, let us skip through it and just see what kind of tasks across different domains like text, vision, and speech. What are the tasks that are covered under sequence labeling models? Some of the models that you are familiar with are, I mean, the simpler models that get solved by sequence labeling models are POS tagging. If you want to do some natural language processing, the basic task that you deal with is tag the sentences for their parts of speeches tags. Right, so that's the most primitive sequence labeling task, and it can be dealt with by any of the workpath sequence labeling algorithms. Okay, and we are going to see the algorithms, this category of algorithms, categorization of algorithms like what we have for conventional classification algorithms. Okay, we have a categorization for sequence labeling algorithms too, and we are going to see that. But what is that we can do with these algorithms is what this slide explains, and these are the typical tasks that are solved by sequence labeling algorithms. POS tagging is a simpler task, and it is simpler in the sense that the two sequences that are to be related, the label sequence and feature sequence, they are of the same size. And means if you have a sentence, if you have 10 words in the sentence, then exactly 10 tags are to be mapped to these 10 words, and usually there is no I mean out of order labeling and all. Usually the labeling is sequential, one word after another word, right? And this can be thought of as most simpler sequence labeling task. And there are other complicated tasks like parsing. Coming up with a parse tree, I mean, it's not the conventional language processing parser and so on that we come across in computer science. It is the natural language parsing. So when you process a sentence in a natural language, how to come up with the syntax tree that explains the sentence well, right? So that's the kind of task it is, and coming up with such syntax trees is also crucial for processing the data. The other tasks are co-reference identification, and question answering is also one task you might be familiar with. There is a Watson Watson and lots of other upgradations that have happened for what this IBM company works in this question answering space, and there is a lot of research that went into to explore the historical things and other knowledge, factual data that is maintained by the learning algorithm, and in such a way that I mean, the machine can search through the answers and stitch multiple things put together to compose one single answer that can be given as an answer. Right? Question answering is a very, very complicated module, and I mean, by all means, I think this can be solved only with some simplifying assumptions. Okay. So question answering is one such task which can also be modeled in the simpler cases. It can be modeled using sequence labeling algorithms. Sentiment summarization is another scenario which is also a case which can be solved using sequence labeling algorithms. One excellent example that is worthy to look at is this machine translation. So in machine translation, you have source language sentences and target language sentences, and you are this. I mean, the moment we are tagging it as machine something, then the task is done by the machine. That means it is a machine learning algorithm, and for it to work, for it to do the task of translation, the learning algorithm has to be given enough examples. And in this case, the kind of task that we're giving the learning algorithm is pretty complicated. So so the number of examples that it requires for it to work to a satisfactory level is huge. So you need basically you need to provide this translation algorithm, uh, thousands of or millions of examples of paired text. And paired text is usually very, costly. Paired text means you have to provide the learning algorithm the sentences which from the source language and the translation in the target language. You have to match. I mean, you have to provide matching pairs of sentences, which is costly to provide. And yeah, this is also one task which can be solved using sequence labeling framework. Okay, and search query correction is another task which can be modeled as a sequence labeling problem. All of us usually when we are typing in the Google, we'll see that we don't write the correct spelling of the query, and we often mistype, and then the spelling is automatically given uh, by the algorithm, that is the search engine itself, to provide you the corrections. Okay, the kind of corrections that usually provided are, you might have broken a single word, which is uh, 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 unintendedly broken by you, but because of this breaking of word into two words, you might not see match in the corresponding documents. So usually when we are searching some phrase, then that phrase is looked for in the underlying document base that Google maintains or Bing maintains and so on, right? So that matching will happen if that word is seen in the other the source documents, right? So that does not happen if there are misspellings in the word, and the misspellings can be in multiple ways. So if you combine the words like United States of America, then without spaces, then it has to understand that it is referring to United States of America, and it has to split it accordingly to match in appropriate places. And one more word that you can quote is baseball is one single word, and if you split it baseball, then all sorts of wrong documents are matched if you don't understand, if the search engine does not understand that this is a single word, right? So some words are split unnecessarily by the search users, and some words are split. They are combined unnecessarily. These are the two kinds of problems that pose difficulty to the search engine, and we see that sequence labeling modules can help in these tasks also. And most applications like speech to text transcription, and I mean several tasks in speech domain are modeled using sequence labeling tasks. Vision tasks also they get addressed using sequence labeling, and some of them are object detection, handwritten character understanding, and then gesture recognition, activity detection, and then image captioning. So given an image, what would be its caption? It's a very important application in computer vision, and it relates actually two different fields of machine learning, whether it is computer vision and then NLP. Okay, so how to generate the captions is a task that is solved by NLP, and how to process the image and capture the features in a way that the machine can understand and process is what the computer vision domain does. And this image captioning and storytelling are two sub problems which are combining the two different fields, NLP and vision together. Okay, you might have heard of several variants of CNNs and so on in the earlier sessions that cover the vision tasks, and now we are going to see some of the fundamentals of solving this sequence labeling problem. So conventional classification approaches, they are regression approaches, they're solved using any machine learning algorithm for that matter. It requires training data. So there are a bunch of examples provided, n examples are provided to the learning algorithm. And you can think of it as a simple task such as uh, identifying the images that contain apple versus orange. Okay, so the label y here is equal to apple for some of the images and orange for some of the images, and there are features that are extracted from the image which are provided to the learning algorithm as vector. Okay, vector values are provided. How this label feature linking has happened is up to the machine learning algorithm, but y is a discrete label, and the task that we have at hand is the I mean it is a simpler. You're given with a bunch of features extracted from the sample, and that vector is to be related to one label. So I mean, you can think of it as a discrete variable which can take values as many as the number of categories in your labeling task. Okay, so that is the task that we are solving when we are dealing with classification or regression models. In the case of regression, it is a numeric entry that we are dealing with as y, whereas in classification, you are dealing with a discrete thing. Okay, so there are a variety of models that solve this problem, and naive Bayes is one of them. And you see that naive Bayes is a generative algorithm which models the joint distribution of these examples, feature vectors versus the corresponding label. Okay. So the model tries to fit the samples to be examples of the joint distribution, and in the process, it is a probabilistic model, and it is simple and efficient, and solves the problem indirectly because it is using the samples to estimate probability of x comma y, and it is solving the problem of finding the probability of the label y given the example x using the joint distribution. So the model as such uses samples to estimate joint distribution, and which in turn, the joint distribution properties in turn help us to estimate the conditional distribution or posterior probability of y given x. Okay, so that is the way this naive Bayes solves the problem, and it is called generative. And more or less, the models that use the samples to be examples of joint distribution are the ones that we can categorize as generative classifiers. All the three other things that I listed here are discriminative basically, and just can you I will just take 1 second and Uh, yeah, so the other models, logistic regression, support vector machines, and then neural networks, they are all discriminatory in nature, and we can see that there are different. I mean, with respect to their efficiency for solving this task, discriminative approaches are by far better compared to the generative approaches, and in particular, the generative algorithm that you see here is coming with some modeling assumption which is a little less effective, and the naiveness in its weight assumption is also something that hits the performance usually, and these other three algorithms, they usually perform better than the classification approach that we have there. Okay, so more or less, all these algorithms solve the problem in to different effectiveness. So, can I click pen? Yeah. So yeah. So here the model that you see here is logistic regression, and you can think of it as a neural network with number of features. Number of units in the input layer equal to the number of features, and the number of uh, uh, output layer. There is no intermediate hidden layer as such, and the output layer is associated with the number of nodes equal to the number of class labels that you are dealing with. So if you are dealing with apple versus orange classification, probably one node is good enough to deal with this task. Or if you are dealing with a multi-class classification, which has more than two classes, then you need as many as the number of nodes is equal to the number of classes that you have in the problem. Okay, so and there is usually when you are dealing with a neural network, you see, the network has some connections and so on, right? So the nodes that you have here, they have connections to all the input nodes. That means there are weights, one for each of the nodes that you have in the output layer. So as I told, the number of nodes in the output layer is equal to the number of class labels, right? So each node here has number of weights equal to the number of features. So if I have a feature vector of length 1000, then a 1000 length weight vector is associated with the class 1 and class 2 and class 3. Okay, so there are there are parameters that do this classification, and the class 1's parameters, they will try to ensure that the examples which are more belonging to class 1, they have higher score to be in this class 1. Okay, ultimately what this logistic regression gives is a probability vector of, if I'm dealing with a 3-class classification problem, then it gives a probability vector P1, P2, P3, whose summation is equal to 1, and which are all greater than or equal to 0. Okay, so that's the kind of output given by the logistic regression, and the learning algorithm is because the kind of framework that you have here is called log linear, and it belongs to the rich set of problem sets that is called convex optimization. This problem can be, the optimization problem involved in logistic regression can be usually done with LBFGS, which is a Newton-based quasi-Newton method actually, to solve the optimization problem, which can converge very fast compared to the neural networks that you usually deal with. Okay, so fastness if you need, then you use logistic regression and capture all the complexity in the feature extraction process, then you get the best accuracy, accuracy as well as performance of the classifier. Okay, so then support vector machines are also some things that are again in the convex optimization framework, but they use not the logistic regression kind of modeling assumptions. They use something called the uh, margins. I mean, the uh, the classification model is usually assumed to be in a support vector machines case. This classification model is usually assumed to be a hyperplane in the higher dimensional space, d minus one dimensional space, if you're dealing with d dimensional data, and that will be chosen in such a way that it separates the samples in the data set of multiple classes uh, uh, by a larger margin. By margin, what we mean is that the distance between the hyperplane and the bunch of examples belonging to the particular class, it has to be maximized. Okay, so the margin, the hyperplane which separates these samples better would be regarded as better classifier, and the support vector machine framework looks for the hyperplane. I mean, search through a optimization algorithm, and it is called quadratic optimization framework, and it is also efficiently solved using some of the learning, the numerical optimization methods. Okay. And non-linearity, if you have in the problem, then it is addressed using kernels. And this is the nature of support vector machines if you are using it for classification problem. And neural network, as we know, it is more complicated, and it can handle the nonlinearity present in the problem that we have at hand, and it achieves that using two kinds of things. One is activation functions, another one is hidden layers. So if the problem is more non-linear, then you use more hidden layers to process the data in stages and form the hierarchical features to abstract out the problem complexity, and ultimately that can handle much of the complications like the ones that we see in computer vision. So if you want to use the same kind of if you want to embed the same kind of complexity in a 2-layer, 3-layer network, the number of connections that you need will be humongous. And for image classification kind of task where you have 224 by 224 images, the model size can blow up, and usually such training will be hit. And that's where your convolutional neural networks, they they solve the problem in a series of steps, and they will be able to solve the problem using stacking of layers. Okay, so neural network is, designing neural network is a engineering problem, and it was tackled well in the recent past, and I think it is covered to some extent in one of the earlier classes that you have seen. Okay, so linear classification is the kind of model that we can use when we have a simpler task that we have at hand, and the task can be as simple as identifying, distinguishing between apple versus orange or dog versus cat, or as simple as that. Okay. But this simple thing can also become complicated depending on where you're capturing the images, and the domain of class labels themselves, and lots of other factors they can complicate this task, and linear classifiers might not be able to do the trick, do the classification well. Okay, so in those things, so one more example where the nonlinearity is needed is the anomaly detection, where you're supposed to build a classifier to identify patterns which are very rare and which are not commonly observed. So anomalous observations are rare, but normal observations are frequent, and most of the data is filled with normal observations. Despite that, how do you train the algorithm to address the anomalous cases? right? That's an important challenge that has been found to be very difficult to deal with from the machine learning point of view. Okay, so that's another example which requires non-linearity. So linearity can deal with the problem most of the time, provided the segregation between the classes is good enough. Whereas non-linearity is needed when you're dealing with more complicated problems. Okay? So just to give you a brief overview of the kind of modeling assumptions that we deal with. Uh, I'll just give you some simple fundamentals of probabilities. Uh, I mean, before we can discuss the models in a common framework. Uh, yeah. So till now, is it? I mean, do you have any questions to ask, or I mean, should I proceed?
Yeah, participants, do you have any queries as of now? Shall we proceed? If you have any queries, please get it clarified from the speaker. Okay, sir, proceed, sir. But no
Yeah.
one. Yes,
Yeah.
sir. Yeah.
Yeah. So now look at this diagram here. So there are two random variables here. I call them as A and B. And if I have a dependency between them like this, what this diagram enables me to do is it enables me to write the joint distribution of, this is called something called graphical model actually, and that is what we are going to discuss in the coming slides. How to model sequences is expressed through graphical model. Okay, so A and B are two random things that we are modeling, and there is a dependency between A and B. If you know A, then you are knowing. I mean, B is completely known based on what we know about A. Okay? So that's the kind of dependency we have. And there is another kind of graphical model called undirected graphical model, where the direction of edge is not specific. And in this case, what we're telling is the state of A or B, given the other one's state, we can, I mean, this is a conditional actually. You can also model the joint distribution also in the same framework. So, so the idea is, I mean, it belongs to something called energy based model family, and the meaning of this kind of graphical model is that the probability of A's state being I given B is obtained by taking the B vector uh, and multiplying it with the corresponding weights that join the B. Okay, so B can be a scalar or a vector. For simplicity, we can think of it as a scalar. So whatever B value is multiplied by the weight that connects these edges, it gives the weighted score of what A's state is. Okay, so that's the kind of undirected graphical model that we can think of. And similar for similar scenario, the joint distribution of A and B can be written as probability of A multiplied by probability of B given A. Okay, so here, I mean, we are starting with probability of A because that is the most independent one, and B state is completely known when you are given with A. So we can, I mean, we can further complicate it by extending it something like this. If I have something like this, then I can further write probability of A, B, C put together. I can write it something like this: probability of A, probability of B given C, B given A into probability of C given B. So because C is dependent on only on B. Okay, B's state is what we need to know to tell what C is. Okay, so this is something coming from the basics of graphical models and probability related stuff. So under this, I mean definitions, we can we can perceive this naive-based classification as, I mean, a graphical model like this. the meaning of this model is that, okay, sorry. So there are multiple links between the label Y and XS. XS stands for features actually. So you have as many nodes here as the number of features, and we are observing as I mean our sample a feature vector in a k-dimensional space. So that's what we are writing here. So your feature vector and its label are mutually dependent. That's what this graphical model tells. Okay, so having obtained the graphical model like this, we will be able to write the joint distribution of xy to be probability of y. I mean, that's the most independent one, and probability of x, the vector x given y, which can be split as probability of x1 given y multiplied by probability of x2 given y into multiplied by all the xk's given y. Right. So this can be written as probability of y into multiplication of I is equals to 1 to k probability of xi given y. Okay, so this is what we can do once we have our I mean graphical model like this. We will be able to write this joint distribution like this, and we can estimate the parameters of the model, namely the prior probabilities of the label and the conditional probabilities, the feature conditional probabilities also. These are also parameters. So the number of such parameters is equal to the number of labels into number of features. So if I have 1,000 features, then I have 1,000 by I mean, if I have a 10 class classification problem, 1,000 by 10 would be the number of parameters of this type, and the model tries to estimate these parameters. Okay, so that's the understanding that you should have when you are dealing with naive Bayes. Okay, so the reason why I'm going into this is I want to show you the commonality between the problems that we solve in classification context and how we can tweak them to a scenario of sequence labeling. So that's the link that I want to bring before you. As I told, this probability of xy is what we are trying to maximize, or we are trying to estimate. Okay, so that is estimated by using the training data. So training data is used for you to estimate the properties of the model. Okay, the model properties are nothing but the conditional probability that you have for feature based on the label. Okay, so that's pretty much the objective that you have for your naive Bayes classification, and it is done by, it is represented by this graphical model. And using, I mean, this is not minus, this is plus actually. So if you see this, it is pretty much similar to logistic regression is what is being modeled like this. And as I told, I can use nodes, I mean, is two-layer neural network to do the same, I mean, to convey the same thing, or I can use a diagram that is resembling like naive Bayes, but the directional edges of dependencies are removed by undirected connections, and using the notions of undirectional probabilities that I have already told you. I mean, when you have two nodes, the undirected model tells you the state of one of these variables as a function of dot product between the other variable versus the weights that connect the two nodes. Okay, so the weight, so here instead of it being a single node, you have a bunch of nodes here, which are the number of nodes is equal to the number of features that you have. Right, so X is a feature vector of k dimensionality, and all of it is connected. I mean, you can think of it as a single node. With k as the dimensionality of it, and all of it is connected to this. Okay, so how do you estimate the properties of y taking one value or other value? It is done by taking a weights vector that connects the nodes here and taking the dot product of this weights with the feature vector. So that's the typical operation that you see in neural network. What do you see in neural network? You have a node here in the higher level layer, and it has a bunch of incoming edges, and you'll have to take the features multiplied by the weights. The weights and features is what you're taking the dot product, and that is the core of its operation. Okay, so you have a bunch of weights that connect to this node, a bunch of weights that connect to this node, and a bunch of weights that connect to this node. The number of such weights is equal to the number of labels. So if I have a 10 class classification problem, I have 10 weights vectors, one for each of these nodes here. Okay, so the number of parameters is equal to 10 cross number of features is let us say 1000. Okay, so 10 by 1000 is what I have as number of parameters for my classification task, and I'm using logistic regression. So the number of by I mean, if you compare the number of parameters, it is exactly matching with that of naive Bayes. So the naive Bayes and logistic regression are comparable in that sense. And if you see here, this is corresponding to weight vector of one class. Okay, this is corresponding to weight vector of second class. So weights are, I mean, the vectors are of size equal to the number of features that you have, which is 1000 for the example that I have indicated to you. Okay, so now I mean, the probability of it can take values of for y can take values 1, 2, and so on. L L is the number of labels that you have, and each of them is proportional to the weights. So if you want to compute the probability of y belonging to class 1, then there are a bunch of weights that connect this node to the features. So you have to take that weights and the feature vector. That dot product gives you a single score, and exponentiate it. That is representing the score of the example belonging to class 1. And similarly, the score of example belonging to class 2, score of example belonging to class 3, and so on. I mean, SL. Okay, SL is the score of it belonging to class 3. These are all found, and there is a final normalization to, because ultimately what we want is a probability vector of P1, P2, P3, whose values can help you to decide whether class 1 has a higher probability or class 2 has some higher probability, and so on. Right. So for that purpose, you usually normalize these things. The scores that you get, you normalize it using simple normalization scheme like S1 divided by S1 plus S2 plus S3 gives you this probability. And when you change the numerator to S2 and divide by the denominator, same denominator, then you get the second term, and so on. So this is how you can get the probability values using the model parameters in logistic regression, and you will be able to solve the problem of classification using this model. Yeah. So so far, is it I mean understood? If you have any issues, I can address them here.
Yes, sir. I hope understood. What
Okay.
we can interpret anything. I
Pardon?
understood percent or not. Participants, if you have any queries, please get it clarified from the resource person. If you have any doubts on the as of now, please clarify from the speaker. They are typing, sir. We are following you, sir.
Yeah, because at the end of the day, I think I should, I mean, at least for the people who are following, I should not pose some things that are not understandable, right? So that's because this is a remote mode of operation, and I think it requires a little bit of feedback. It's not a well sync feedback. Okay. Yeah.
Yes, sir. That I think we are following, sir. Proceed, sir. Thank you.
Yeah. Okay, so let me, yeah. So logistic regression is, I mean, in terms of its I mean, core modeling process, if you observe, the number of parameters is equal to the that of the naive-based model, and there is a parameter vector one for each class. This is class one parameter vector. This is class two parameter vector, and so on. This is class L parameter vector, and there is one vector associated with every class, and together they are giving us the probability scores, and there is a slight normalization that happens after this scores get computing. I mean, that's what the standard operation that you see in logistic regression. Okay, so the core operation that you have to observe is that you have feature vector x, and there is a weight vector associated with a label uh, 1 or 2 or something like that. So this is a label 1, this is label 2, label 3, and so on. The number of labels is equal to L. Okay, so one vector is associated with every label, and you are doing dot product between that feature vector and the same feature vector and the parameter vector, which gives you some sort of score, or I mean, if you exponentiate it, then you get the score. So the core of its operation is done by this dot product, which is a linear operation. So even in SVM case also, the same kind of linear operation is done, and there is no exponentiation in the context of SVM, but there is a maximum margin constraint on the kind of model that you are looking for. Okay, so that's the difference between these classifiers. You don't have such dot product in the naive base. You have slightly different assumption in naive base, which is doing the trick for you. And sequence labeling is the model that we are looking for. If you look at the task that you have here, you have a sequence of entities x1, x2, and so on xt to be tagged and associated with the corresponding label. So this is called feature sequence. This is called feature sequence, and this is called label sequence. So feature sequence is something like, I mean, you can think of it as a sentence. Okay, so the sentence is, I mean, something like, I went to Australia to watch a movie, the cricket match that is going on. Okay, to watch cricket match. Okay, let us break it here itself. So I is standing for one word, want, went is another word, and so on, and the labels associated with them are, I mean, noun, verb, and particle. Then there are lots of other entities here. So as
Yeah, dear participants, due to some problems, sir is disconnected. We'll just wait for a few minutes. We are communicating with him. Wait for a few minutes. Sir will rejoin the meeting. Yes, participants, Dr. Nagesh sir is in session. Sir will continue the session. Sir?
Okay. Yeah, so if you want to look at the complexity of this problem, yeah, I think some interruption was there. So we were looking at a hidden Markov model, and uh, the thing that you can see is that each entity in the sequence is associated with one label, and that label can take any of the values from 1 to 10. And in that sense, if I have a 1,000 length sentence or 10,000 length sentence, then the number of possibilities for the labels are, I mean, if I have 1,000 length for that example sake, and each label can take values from 1 to 10, then the number of, I mean, states that I am exploring is equal to 10 power 1,000. And it is pretty much dependent on the length of the sentence. So it can be 100 or 200, and 10 power 10 power 1,000 is a huge state space. So the sequence labeling models, I mean, face a much harder optimization problem of searching through the state spaces for which this probability is to be maximized. So all that you're looking for is the y label sequence y that you're assigning to the sentence. It has to be in some sense given as the most likely label sequence by the model. And hidden Markov model is one such model, and it naturally extends this naive base with some simple extensions. This part of the model is pretty much same as the naive base, and this part of the model is the extension. So there are conditional dependencies between y's, and by the definition that I have given for you to write these conditional dependencies in this manner, it allows you to write the conditional the joint probability of x and y, where x and y both of them are sequences, not a single. I mean, y earlier is in classification scenario it is label actually. In probably I mean in sequence labeling tasks, they, both of them are sequences, and you can see that the joint probability can be written like this, and the model parameters can be estimated from the training data. So there are two kinds of parameters. One is label conditional probabilities, feature label conditional probabilities, and label conditional probabilities. If I have a length 10 vocabulary, then this kind of features will be 10 cross 10, and this kind of features will be vocabulary size into the number of labels. Okay, so that would be the number of features. And conditional random field is a similar kind of model. I mean, extension for logistic regression that we talked about. And there are two kinds of features that are taken. One is the label condition feature associations are captured using this feature vector here, and label associations are captured using another feature vector g of y. And basically, when we spoke about logistic regression, we identified that the basic operations that we see is that the features versus the weight vector associated with that task is what the core operation is, right? So if you have a label y, then there is a parameter vector associated with that label, and the dot product is done with the feature vector. This is the fundamental operation that we have done in classification tasks. Because the labels are, I mean, many, you cannot do exactly in this manner, but we actually capture all the features from the feature label associations in the form of a vector, and we use a associated parameter vector called omega, and the feature vector is called f of xy,
Sir,
and we
please share the screen, sir. Please share the screen, sir.
oh, I will anyway share the slides actually.
Yeah, yeah.
So yeah,
Okay,
sorry for this, when
okay, okay.
I was not looking at this part. Okay, sorry. So the parameters and features actually they interact in the form of dot product, and that forms the basis for conditional random fields. And the same algorithmic framework as that of this logistic regression, we can use the same kind of thing to even use. I mean, you even model the conditional random fields. So to summarize, classification algorithms versus sequence labelers, you have sequence labeler called hidden Markov model for, as opposed to naive based with similar modeling assumptions, and conditional random field as opposed to logistic regression using a similar kind of framework. If I have some 10 minutes, then I think I can complete the example that I have planned for. Is it fine? Uh, yeah, okay. I will share with you the code for this, and I mean, there is some more thing that can be covered, but I mean, in the interest of time, I think we will stipulate our focus onto the conditional random field based exercise.
Yes, sir. Continue, sir.
Yeah, yeah, I am just doing that. I am just opening the notebook and yeah, that's it.
Okay, okay.
Uh, I think notebook is visible, right?
Yes, sir. Yes, sir.
So
It is visible.
the this toolkit is called PyCRF suite, and yeah, let me, uh, yeah, let me show you the kind of task that we're dealing with first, and then very quickly we'll go through the. Okay. Yeah. So this, I mean, you see this sentence here, which is written vertically. This dataset is called CoNLL 2003 dataset, which is meant for name entity recognition, which is one of the sequence labeling, when used as one of the examples for sequence labeling. And you see that there is a sentence written in the first column of this file, which is EU rejects German call to boycott a British lamb. This is one sentence from that corpus 2000 and COINL 2003 named entity recognition task. And if you see this tags, the last column here in the third column, IARG indicates that you are inside the organization entity tag. So the task is to identify the entities associated with the words. EU is a entity, and that's the meaning of this tag. So this tagging is actually useful in lots of tasks like information extraction. You want to extract entities from text that are observed. Initially, I showed you the way this chatbot was working, right? So it gets some input from the customer, and from that input, it has to extract relevant fields of information, right? So that is nothing but information extraction, and all those information extraction tasks can be modeled as sequence labeling tasks like this, like what I have shown here. So there is one sequence that is given as input, and it is to be related to the output sequence, which is given in the third column. And there are a bunch of tags that are associated with the entities that we are interested in. Okay, so some of them are associated with O tag, indicating that we are outside of any tag that we can follow. Now, this is a training data set, and there are some, I think, 60,000 sentences in the data set, and you can read the dataset using the code that I have provided here in the form of this notebook. Let us run through the code. Uh, 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 the Python notebook that we have to run through this example. Okay. So I am now trying to upload these 3 files, which will be again provided to you. Let me just say a look. Yeah, it's getting uploaded. Let me just upload it. Once I upload it, I have to move it into appropriate file folder. Yeah, it is done now. Yeah, so that step, moving of these files into appropriate folder, is also done. Now we have our training data provided in the form of a list. So the dataset size is this is what so 14,986 sentences are there in the training portion, and 3,000 3,683 sentences are there in the test data set. Then you can look into a specific portion of it and so on, and then you can actually build features from the I mean, this task is actually a very tricky task, because to associate with words the corresponding labels, the amount of signal that is available is very less. Right? Most of the times, when you come across the sequence labeling task, you don't see that the same words that are used in the training data are exactly used for in the test data also, right? So if you have built some machine translation algorithm, then it is unlikely that your machine translation algorithm should work on exactly the same thing that it sees the source language sentences seen in the training data. So the test data will be something altogether new, and that's where the trick is. And machine these kinds of sequence labeling models, they have to work with such tasks, and you need to carefully engineer this task of composing these features, and this code that you see here is exactly doing that. And once you are done with that features composition, then you can actually train the algorithm. And it's not a big deal. You can train this stuff. I think it is worth just to wait for 1 or 2 minutes to complete this training process. Otherwise, this discussion will not have you any, I mean, will not give you some tangible thing, right? So just I just try to put the training data that can be consumed by the learning algorithm, and this kind of learning algorithm is LBFGS with some slight variations. Okay, so this is the step that trains the model. Okay. So compared to the amount of time it is required to train this model, when you compare it with the LSTM kind of models, the time it takes is very less because of the linearity in the modeling process. So you see that the model relies on dot product between feature vectors and then the corresponding model parameters. So that's pretty easy to do. And rest of the things, once you have the model with you, you can actually do the tagging, or you can try out how good your model is working with respect to test data. All those things you can do to evaluate how good your model is. So our training is done. Now we can test, how good it is doing for example sentence, and also uh, for the whole test data put together, we can evaluate its performance. Just a minute. Yeah, this is the kind of accuracy statistics that you can obtain for this data set. And F score is what you should look at. And the even if you see the weighted F score, then it is roughly around 0.79. And it's not so great. But this is the model initially used in Coinel 2003 datasets. I mean, task, and in the later part, they have used such a CRF-based models, and they have done some lot of feature engineering to tackle this problem. And you can see LSTM-based libraries. I can also send you the kind of links for that. LSTM-based worked example for solving the same problem, and it achieves around accuracy of 90.91 F score. The benefit is that it uses something called word embeddings, and NLP has changed a lot ever since word embeddings are introduced into NLP literature. Okay, so that I can give you as one more Python notebook that you can work out. So this is the Python notebook that I can share with the organizer to to give you some hands-on with respect to this sequence labeling task. I think I am on time, and some 2-3 minutes is what I have spent extra. So if you is it fine? I will share with you the PPT as well as the content with the organizer. I think that should help you to go through what I spoke and relate it. Okay.
Yes, sir. Yes, sir. Yeah, that will be better, sir. We will share with them.
Yeah. I will share with you the task specific Python notebook. I have it with me, and send you along with the other things. Okay. Yeah. With that, I think we have a crunch of time, and I think all that we can do is this CRF, and one example we could work it out, and the task that we have worked out with is name identity recognition. If you have any queries, you can ask. Otherwise, we can leave.
Yeah. Yes, sir. First of all, thank you, sir. Thank you for accepting our invitation and spending the time to deliver the session to our participants in the AICT sponsored HTTP. Now I am requesting the participants to clarify our doubts regarding this particular session from the resource person. If you have any queries, please get it clarified from the speaker. Sir, okay, I will ask on behalf of them. What is the scope of research in this particular area, sir?
What I gave you is some primer actually. An introductory session on sequence labeling.
Okay.
Labeling is found. It has found extensive applications, and today also, lots of papers get published using sequence labeling, and it is an exciting area actually. So, when you know the trick of relating features to the tune of sequence labeling task, then you find it extremely exciting, and a lot of scope is there for research. Okay. Question answering, there are thousands of problems in question answering which get solved, and there are lots of forums which extensively use these kinds of ideas. And EMNLP is one conference where these papers get published using the
So conference name, sir? Repeat again.
EMNLP, CIKM, WWW, and then WSTM. lots of conferences are there which specialize in this domain. And even Rex is also publishes some papers that focus towards ML uh, that is underlying this. There are a wide range of applications. Area is, I mean, if you pick one thread carefully, then you will get depth, and you can use it for exploring the other places also.
Sir, I have a question. I'm working on evaluation of descriptive answers. So, will this be useful in that area? Like when we want to compare given a student written answer to a key answer.
Yeah, exactly. This is what these question answering kind of tools also do. But I mean, as such, this sequence labeling model that I demonstrated to you that uses this CRF is basically a linear model. So the problems that you are referring to are more non-linear in nature, and they are used. I mean, there are lots of innovations that are happening in this world in this space, the problem space that you're looking for. There is a Stanford-based research group that works on question answering, and there is a researcher who specializes in these things actually. You can refer to his works on question answering using dynamic co-attention networks and so on. So there is attention mechanism that is used to relate the two kinds of things. So you have a question and an answer, right? So this question is related to I mean, this answer is related to the question, and the way you structured your question, the answer will also be like that only, right? So to relate that, you use some kind of attention from question side and answer side, and it is called co-attention mechanism. Okay, so there are lots of works that are going on. You can look around, and I think that gives you a. I mean, it's an exciting area, and you can actually do some contributions in that area.
Sure, sir. Thank you so much.
So, Namaste, sir. This is Anant Narayan speaking from Hyderabad. Relating to sentiment analysis, sir,
Yeah.
and language processing, both are interrelated with each other, sir. And in that one, writing programming language using Python, R language, and statistical analysis system. SAS. In these three, we'll get the same output, sir, or any changes in the output?
Uh, okay, your question is first part of it is sentiment analysis. Can you rephrase the first part of it? What is your question finally about this sentiment analysis?
And language processing, sir, means if you take Sanskrit or Arabic or French, there are naming conventions will be there, sir. If you take statistical analysis system, means in Sanskrit and French, some dots, if some lines will be there, sir. If you take Japanese language also, in that one, if you take Arabic,
Phonetics.
yes, sir, exactly, sir. Left to right, right to left will be there, sir. In that one, ASCII standards according to the naming convention will change, sir. Regarding to that, in sentiment analysis also, relating to language processing, if you write the programming code or language, is the output will be same in three languages, or it varies from R on SAS and Python programming, sir?
Actually, this, I mean, what is underlying these toolkits is definitely varying from one toolkit to another toolkit. And as I saw, I mean, these frameworks evolving, I think pretty much nowadays Python is what people use, and because it has a lot of connectivity to free tool base. Then if you see R, the free version of it is still having lots of memory issues, and if you see anything like this done in R, it gets stuck usually with memory contention, and that's the reason why people use Python-based toolkits, because it is a programming language and it has more bigger community, and that's the reason why people use Python. But as far as I mean output relatedness is concerned, as long as these underlying libraries are using the same kind of methodology or numerical optimization routines, the output should match. But when it comes to neural network, surely it won't match, because It is a local optimization, and there are multiple minima that are there for your optimization problem, and it cannot match. It's just over a period of time, and you run it for several iterations, and till your cross validation accuracy is better. But it cannot be bettered, right? That's a heuristic only. Nothing can be done for that.
Yes, sir.
So
Thank you, sir.
you cannot have matching outputs strictly.
Thank you, sir.
Yeah. Is that yeah?
Yeah, any more queries from the participation? Anything you want to know? Yeah, sir will give you the clarifications for your doubts regarding your research. You can type it in the chat window. Otherwise, you can unmute yourself and you can ask the question. Sir, do you have any popular data sets for this, sir?
Actually, this data set is again used in recent explorations by people, and they show how the accuracy that we see, or score that we see here, using simple approaches like CRF, it can be bettered up to 0.91 by using LSTM as a workhorse there. And there are, lots of other data sets also there. But just for the sake of exploration, somebody, if they want to know how LSTM works better than the simple model like CRF, I think that's worthy to look at, right? So I have used this data set for that sake. And anybody who is trying to understand sequence labeling, they initially start with this kind of data set only. There are other data sets and other problems also. Wide range of problems can be addressed by this framework.
Okay, sir. And I think you are already reading the question. Sridevi is asking, like, hybrid machine learning and reinforcement both are different or the same?
Hybrid is a little, this kind of word. It is used in lots of senses, madam. And I think reinforcement learning is where your, environment. There is a policy gradient and so on. There is a policy that you use to, update the model parameters and so on. So that is a slightly different framework, and it suits more in the kind of this chartboard kind of environment rather than any standard supervised learning frameworks. But most of the times, your supervised learning framework will do well for the kind of task that we are looking for. And there are very few use cases, in NLP, like chatbot kind of environment. But other than that, hybrid machine learning is something that I could not get the intention. What is the use of this hybrid word? I'm not sure whether you're looking for, a hybrid of learning techniques or hybrid of models. There are lots of things there, right? So, because depending on that, this hybrid machine learning might mean different things. And data sets for sentiment analysis, there are a wide range of data sets for sentiment analysis. Uh, there is a initial data set that is provided by Bo Pang Lee, and then lots of data sets are provided by a researcher called Bing Liu. He has written even a book on sentiment analysis. And there are data sets from Stanford, and you see, if you go to their website, you see lots of data sets are there on sentiment classification. And there are separate data sets on sentiment regression, rating regression kind of modeling. So this is a slightly different problem scenario, where the model has to address. You usually when you see Amazon and other websites, right? There are aspects that are modal, and for every product there will be some fixed set of aspects for which these reviews are related to. So this review is related to this aspect by this value. That is what this kind of analysis. It is called rating regression analysis. So your overall rating is related to aspect specific ratings, and those aspect specific ratings are further related to the underlying review. So some hierarchical process has been put to relate these things, and those kinds of things will help you in not just sentiment classification at the higher level, but further useful analysis you can do using rating regression analysis. And there are lots of data sets out there to do this rating regression analysis also.
Sir, can you suggest how to get the data set for sentiment analysis? And one more question from Anant. Yeah,
That's what I was addressing.
yeah, you already addressed it, sir. Yes.
So rating regression, I can give you a link here itself. Yeah. Just a minute. There is a data set here. Yeah. So there is an author website also. This author is Hangwing Wang, and their team has done some good work on rating regressions. And it's a very exciting problem actually. There are lots of papers on this problem, and the basic versions are published somewhere over a period of some 5 6 years. 10 years. You see a lot of research that has went into this, and lots of possibilities are there for you to better there. Okay, so this is one problem area that was explored by large number of researchers. And anxiety disorder. I'm not aware of this anxiety disorder problem, but this is it some disease? Maybe is it some text related problem, or because I, I personally don't know. Okay, so if it is text related, then you can always get plenty of data sets, because when anything that is related to some specific disease and specific image kind of thing, it is difficult to obtain. But if there are discussions in the social media forums about some diseases, and if you want to analyze that kind of text, definitely the kind of models that we spoke here will be helpful. And usually you see that there are fair number of data sets that are available, but specifically I don't insomnia or some there are some sleeping disorders that are researched by people through social media postings and so on. They are also useful. They are also something that can be addressed using the model that we talked about in this session. Yeah. I think,
yes, sir. Yes. Sir, for better future, which one we have to select as a research area, cloud computing or machine learning?
No, madam. This is a wide. This is a research question for me. This is, I mean, very very wide in terms of what is your perspective. This is, I mean, you want to get some good research problems. Both the areas are. Machine learning is something that has a wide prospect, and it has its own problems that can be addressed using in the area of cloud computing and image processing. Lots of areas are there which get addressed by machine learning, but I mean, it's up to the researcher and the potential and the kind of guide one gets and so on. Lots of factors are there for you to decide your research area. So first you find some reasonable place where you can work, and then guide mostly the, I mean, based on his expertise, I think one has to get onto research areas.
Yes, sir. True, sir. Thank you. So, with this, we'll conclude, sir. And thank you, sir, for sharing your profound knowledge with our participants. And it is our pleasure to have you as a resource person to this STTP, sir. Thank you once again. Thank you for accepting our invitation and delivering the talk on sentiment analysis. Thank you once again, sir.
Thank you. Thank you for giving me the opportunity here. And yeah, all the participants, wish you a good luck in your endeavors. Thank you.
Thank you, sir. Thank you, madam.
Yeah. I request the participants to fill out the form for the afternoon session. We have posted in the Google Meet chat window. Please fill out the form. And that's about today's session. And coming to tomorrow's schedule, tomorrow we have a topic on. We have the sessions on deep generative models for computer vision by Dr. Subramaniam, IIT Roper. And after that, scope of research in deep learning. So this talk will be by Dr. E. Damodar Reddy sir from NIT Goa. And in afternoon, we'll have the valedictory session from 2 to 2:30, followed with the online assessment exam. So exam is from 2:30 to 3:30. So that is the schedule of tomorrow. And I thank all the participants for your active participation today. Thank you once again. Now we have session on deep learning for autonomous.
Yeah.
Stop your presentation. NSK.
Safety means our system has to detect to that our vehicle also should lines, white lines. These are the lanes. Some gaps are there. Right. These means train the system and edges. So we have lot to understand, but we need to train so that we can avoid this. What is that called? Accident, right? So anyway, here we are assuming these are one way, not two way, because in two way these has some different. Then we will black color and this is having given image, right? Gaps. So anyway, this trees information, right? We require only the road information. Means whether what about the lanes? The lanes will be on the in the down of means in the upper lower half of the image, right? So simply we will blur. Sorry, simply we will mask out this upper half of the image, right? So these are the first four steps. Now coming to the fifth one. Next, we'll apply some half transformation.
Holds PhD degree.
Anand,
The human,
1 minute.
yeah, it's fine, sir, it's fine.
Someone is sharing. Maybe accidentally it is happening. We will do it.
This one is first used here, whatever is, color, right? Colors based on your model. So which will generate us these numbers. Like if you observe here, it will give us some numbers. So you can see here, after we'll go the threshold, we'll consider so this is the complete result of our model. The first step is the initial image. If you observe, we'll have one more.
Hello.
Hmm. Which are not on the road
welcome you, sir, to this AICT sponsored online short-term training program on machine learning and deep learning techniques.
Any of the problem of label